Thank you so much for being here, Anthony. And your company is called Verdant Structural Engineers, and you're one of the leading natural building alternative construction engineers around that I know of. You co-authored some of the latest natural building codes, like the Cobb codes, and it's generally, one of the key players that I see here. So thanks for being here and leading the way.
Yeah, sure thing. My pleasure. Thanks for having me, Scott. And nice to see everyone. I assume there's almost always some owner builders or aspiring owner builders. I heard there might be some architects in the on this class. Or there.
We have mostly aspiring owner builders. A couple people here have some training in architecture and are, professional builders. And, people are pretty wide distribution across the whole US.
Great. So yeah, my name's Anthony Dente. I'm principal and owner of Verdant Structural Engineers and Verdant Building Products in Berkeley, California. I grew up in Pennsylvania, though, and we work all over the country. I'm licensed in a lot of states now, primarily because people have a hard time finding licensed engineers that are willing to work with natural building, deep green building, low carbon building materials, especially more alternative ones. This is some of my team at Verdant. I feel very lucky to have these people by my side, and anything I tell you today that I did, it's really that we did. And good collaborators make the world go round. I couldn't believe that more. So I have 200 on here. I think we've surpassed 300 custom natural building projects. These range all over the place, and it's hard to give numbers like this, but because some of them are very small, and some of them are quite big, and some of them are really radical, but some of them are like just a little radical. And so, which ones do you put on the list? So, I don't know. Don't overthink that number. But here's some examples of, on the top row, a lot of straw bale there. There's I believe to the first one to the right is a straw bale wrap building on an existing structure. There's on the bottom we have a couple Cobb buildings. The first Cobb building in Berkeley, California. That was a kind of big milestone. This one to the far right in the bottom is in Topanga, California, near LA. We're just hitting the hard part of plan check response right now with that one. It's an adobe building, pretty fancy. Topanga's a nice place. They build fancy things nowadays down there. But here's some of our early pursuits with prefabricated straw construction on one-off custom buildings, some rammed earth here. Now, on the bottom left, there's a structure that just showing how we can combine a lot of materials. That's has dominant classic wood framing construction portions. It's got a whole straw bale wing. It's got the watershed earthen masonry unit, cinder block CMU replacement early in that product's development. Here's some bamboo construction, a project we did, earthquake rebuild straw bale in Nepal. I'll just right now, if there's really any building material, alternative building material in the natural building space that you can think of, or system or process, we've probably messed with it and tried to get a permit for it. And so if there's anything I'm not mentioning that you're particularly interested in, please ask about it, because I've likely at least made an effort for it. And that's both like something I'm really happy about and probably a personality flaw, because it doesn't always go well. We've learned a lot of lessons through the years in working with these materials. I just started a new company. I never thought I'd be starting a company that was a building products manufacturer, but I'll talk a little bit about this later. But we got some money from the EPA to try to make a prefabricated wall panel using straw bale techniques, a carbon storing system that's more applicable to the wide market than full bale construction is. And so, some natural builders are really interested in this type of thing, and some of them, this is like a box and a square and getting into the corporate commercial market, and we don't want to hear about that in this class. I don't know. We can talk about that if you want to. I'm the vice president on the Cobb Research Institute. which kind of got me into research in the first place. And we'll talk a little, and then code development. But there's all kinds of great natural building organizations across the country that I work with very closely. The Earth Builders Guild down in New Mexico, the Natural Building Alliance, who's having their conference coming up in October. I highly recommend going. I have an opportunity to go this year. CASBA, the California Straw Building Association. And then there's folks like Cal Earth, the Super Adobe Institute down in Southern California, where they're engineers as well. But I work with most of these organizations, at least with code development and other things as they come up. I just finished, I mean, it feels like I finished it a while ago at this point, but writing this book on cob construction for New Society Publishing with Michael Smith, who was a co-founder of the Cobb Cottage Company with Yonto Evans, and my close colleague, Massey Burke, who's a real rock star in the space. I feel like we overuse the term rock star when we're not talking about real rock stars, but she's really great, doing a lot of great work. Started as a natural builder, and now she's a Verdant employee now and a close collaborator of mine as a material specialist, and has contributed to some of Bruce King's books on new carbon architecture, low carbon building, and kind of the forward movement he's been pushing with Chris Magwood on that front. But this book is out in January. I mean, maybe I'll try to put in the text the link if anybody. I think they got 20% off right now. This is my pitch. This is the advertising portion of the show. But it's going to be a big step forward for building science-based information as far as books on the subject are concerned, because we've been doing a lot of testing that's pretty much never been done before to that level and that rigor on this material over the past 10-ish years, and which was part of the reason we got a code passed in cob construction. And I say I work with all these materials. I don't have a favorite, and I don't think that cob construction is the best choice for every project. I mean, Scott and Harry were just talking about the benefits of this other Portland cement based system, and so I am try to be as pragmatic as possible and find the right solution for the right project. And I mean, part of the objective of this book was to also say when cob isn't a good idea. And so I can go anywhere. I have this general flow, and I like to move quickly, but if I'm going too fast, just chime in, please stop me. Let's talk about something. But I like to start with building codes, and then kind of move into structural systems, and then move into testing and our experience. We kind of at Verdant a while back, I realized we had this triangle, this three-prong approach where we're design engineers. People hire us to engineer their building to help them get a permit, or to help them feel safe that it's not going to fall down in the event that they aren't getting a permit. And getting more buildings on the ground, especially of this type, low carbon, deep green buildings, is something we're passionate about. We just want to see more buildings built. And the more buildings that get built, it normally perpetuates itself and helps, you find out the hurdles. But we find out the hurdles we hit with building departments and even running calculations and doing designs, connecting things. These natural building systems, I've found the complicated part is not the cob, it's not the wall, it's not the thing we call the building. It's a cob building, but it's just like, yeah, but it's got a concrete foundation, it's got a wood roof, it's got all these other things in it, but we call it cob. And it's often the cob that's not the hardest part. It's getting in and out of the cob. And sometimes it's the other goofy stuff that, the interesting people that are brought to these materials throw into the projects. And it's very common for a project to, like, the cob might not even be the most radical thing you're doing. It's your cantilevered green roof that you're growing pear trees on top of that it makes things. So I caution people, like, when you're going for an alternative building, it's nice to only have one or two alternatives. If you want the most radical foundation, the most radical wall, the most crazy roof, and it's and like windows everywhere, just pick your battles depending on where you're at. You might be able to do that if you're in a rural area in a light seismic zone. Whereas if you're in a high seismic zone and in, you know, the middle of LA County, the building department's not going to, you know, make your life easy, and it might. So that's that. But I wanted to bring up, I don't know, for those of you trying to get a building permit, if you aren't aware of this chapter, you should be. It's the alternative materials section 104.11 in the International Building Code. Now, your different states might not call it the International Building Code. In California, we call it the California Building Code. We tweak a few things and then call it that. A lot of states do that. I think Oregon does it. But everything's pretty based on the International Building Code, which is written by the ICC, the International Code Council, and they also write the International Residential Code. The building code can be used for any structure, and it's a generally strength-based and somewhat performance-based code, whereas the residential code is a prescriptive code that tells you, okay, you're building a building that's 30 feet by 20 feet, then the rafters, if you're using this lumber type, need to be this big, and done. You have to do that. Whereas the building code says, well, rafters of that type, they're this strong. Go ahead and run the calculation and determine how like wide or thick or weird shaped you want to make it in order to make that work. And so there's more flexibility in the building code. But this section, as a lot of things in the building code, is a very small section, but carries a lot of weight. And you can get hung up with things in the building department that, or in the building code, that have so much text, and you're like, I don't want that. Like the steel version literature in the Cobb Code, in the Appendix AU in the residential code. Some people kind of really zoom in on that and don't realize that there are options for natural and unreinforced systems in lower seismic zones. But it's really easy to say that. You just say it quick in the one section. It's there at the top of the table, and then you move on. And so don't miss the important stuff. This is an important thing. And this section states that as long as you can prove to your building department that your material meets the intent of the code and is safe, that the building code itself isn't here to prevent you from building with that system. So some jurisdictions don't even know that exists, that section. And it's very powerful, but it still gives the building department a lot of leeway to essentially say anything you've presented them with doesn't satisfy them. But normally when you get the right information, you got the science behind you, you got a licensed engineer, licensed architect if you need it, we've never been unsuccessful in getting an alternative material permitted. Sometimes there's been compromises people haven't been happy about, and sometimes the process has lasted longer than people want, which either means that I'm kind of donating my time or the client's picking up more. And you got to be aware of that, navigate that, and anticipate that as much as you can. But like I said, we've never been unsuccessful in getting one where there's a committed client that really wants it. Here's the like a general summation of all the natural building codes that exist in the United States. I think I have the New Zealand codes. There's a lot of prescriptive natural building codes available internationally. Germany's got a good one, a number of them in Europe. There's some information in India, but almost very, very few, if any, of these domestic codes existed when I started practicing 15 years ago when I got out of college. And I've been the lead engineer for these efforts. And we'll also, I don't have our Adobe effort on right now, which I'll maybe talk about in a minute. But then I've played a strong role in these others here in blue, but and code development's really, really fun, and also pretty boring and dry. And you go to these places and you testify, and you have 2 minutes to speak in front of the committee. And I forget, this is the Hempcrete code that I was the lead engineer on. And I think we were in Rochester, New York here. They set up the same setup all over the country every 3 years when they do the cycle again. And it's the building codes, they're hard to deal with. It's not easy to get things adopted there, but it is a generally democratic process where anyone can propose a change, and you get up and testify. But people testifying against you who might not know even really understand what you're talking about have a somewhat equal amount of time to speak. And so you have to have your ammunition ready to fight that. There's been people that have stood up and spoke in opposition to Cobb fire ratings who later stood up again and admitted that they thought we were talking about straw buildings, which I know that there is straw in Cobb, but it's an interesting process. Here's everybody voting yes to the passage of the hemp codes. It's always nice when you succeed. Here's part of the team that was there testifying. And that's the U.S. Hemp Building Association, another organization I didn't mention. There's also the Hemp Building Network now. Some of them branched off and created that, but people working nonprofit style, low budgets, trying to get these building systems forwarded. So now it's like, okay, all these natural building systems. I can talk about lots of conventional building systems. My company, we work from small residential to mid-rise mixed-use commercial. I have probably our biggest building is wrapping up construction right now, 5 stories in Berkeley. And so happy to talk about, green aspects of conventional systems. But speaking from a natural systems side, there's kind of 3 general categories structurally that I put these in. And one is systems that are like wood, and that's hempcrete, post and beam straw bale, or baub straw bale, bales on end between studs. And the newer system where people are comfortable in certain environments, most environments in the United States, putting plywood on the exterior of the bales, and then light straw clay, where all these systems, their earthquake or wind resisting system and their gravity bearing systems are all wood. They're like you're building a wood house, but you tweak it a little. And if you go with a regular engineer or regular design professionals that don't really know those small tweaks, there's not many of them, but you make sure you learn up on it, because there's little tweaks that really make it work. If you're able to keep your studs at 24 inches on center for most of these systems and not do 16 inch on center, make sure your contractor, when they're framing out your house, looks at the plans and sees that you wrote 24 inches on center, because they're pretty used to putting them at 16. This happens all the time. And then, second system are things that are like concrete or like CMU. SMU. Yeah, I forgot. I caught this the other day that there was a typo on this slide. Concrete masonry unit, cinder block is a common term for that material, but the adobe, Cobb, CEB, earthbag, super adobe, these are things that we use the concrete code as analog for when we're running calculations, and use the concrete ASTM standards when we're running tests on them. They're mass wall systems. They're heavy, but they're strong. And maybe now's a great time to mention that for those that are in higher seismic categories, which you might be, even if you don't think you are. We work closely with the 3D Cobb printing company, Terran Robotics in Indiana. What's his name? Alex Summerall out in the Tennessee area. This Cobb, I forget his channel's name. Sorry, Alex. But he's getting folks in contact with us. But we find there's parts in Indiana and parts in Tennessee, especially when you don't have great soil characteristics underneath your feet, where your size design category C. And why I'm talking about this is if you're building a mass wall where your walls are really massive, mass times acceleration equals force. And so earthquakes are an acceleration of the ground, and it's your wall's mass that creates the force that your wall needs to resist. And so I'll talk a little bit more about that, how we've been studying it in labs, and looking for ways we can use these massive walls to resist the problem that they're helping create. Most concrete systems, they're super strong, 3,000 psi minimum, typically, and if not much more. And they're dragging a lot of load from the rest of the building to these really strong pieces. But with Cobb and adobe, the material itself is not as strong. It's around 100 to 300 psi commonly. CEB and rammed earth buildings that we work with can range from 800 psi up to 3,000 psi, depending on the stabilization. Another topic we'll talk about in a little bit. But the I where was I going with that? They're not dragging a lot of load from the roofs. Typically, we use light roofs on these. Some people put vegetated roofs on. So it's really the wall that's the problem, which is pretty unique about these buildings amongst contemporary building systems from a structural engineering standpoint. And so since the problem is generated here in the wall, if you can resolve it within the wall, the subject I'm kind of hinting towards, but not saying, is maybe a rocking shear approach, which anyway, I'll get to that in a minute. Well, I'll finish here. There's one other like kind of category, which is this unique sandwich package system. SIPs, structurally insulated panels, are a structural sandwich package where you have interior and exterior skin that are strong with a ductile inner core. But the reinforced plaster straw bale system, which is the main lateral system in Appendix S for straw bale in the International Residential Code, which my business partner and our senior engineer, my long-term mentor, Kevin Donahue, was one of the 3-member task force that helped write and defend that code when it was initially put in. This is, somewhat unique system. It's a sandwich system. You have the plaster, the reinforced plaster. There's a lot of mixed opinions about how practical this system is, and I can talk about those if you're interested. There are many companies doing prefabricated systems. If particularly straw, new frameworks, our friends and our friends at EcoCocone, who are EcoCocone's based in Lithuania, but they have a U.S. presence now. They're still shipping from Lithuania, but we engineer projects with their system a lot, and we think it's great. I can talk more. Bamcor is another great option. Where they're barge shipping, low carbon barge shipping bamboo up and creating these sheer, very strong wall panel system. But I was realizing that the straw panel systems were not, all the straw systems, they're so wide, and it's a giant fuzzy block you have to deal with. And if you got the time and you got the labor, it's wonderful. I love straw bale building, but just time and time again, you run up to a building officials or developers or contractors that just look at you cross-eyed when you tell them you're going to build a 16-inch to 2-foot thick wall. And I realized that this thing called Small Business Innovation Research Grants existed, and that I was working my butt off with all these nonprofits on shoestring budgets, and that the government had all this money, but you had to be a for-profit company to get it. And then I realized that we were a for-profit company, my regular company, and we're, for better, for worse, we're one of the biggest for-profit natural building focused companies in the States. And so we applied. We were thinking of all the ideas that I had floating around. We had a lot of people having us build kind of custom, one-off, very project specific prefab straw systems. We were engineering them for them and working through the details, but we got this chunk of change to think about, what if we decoupled this from a project and thought about what would make this system the best for the most amount of people. And so we're thinning out the panel, optimizing our straw matrix through manipulation and implementation of the straw. And obviously it's going to be the most earthquake compatible straw system, but its thickness and its weight, and then its cost. We're going to be having these pre-manufactured on assembly line machines, which again, kind of goes against some of the core philosophies that some people, bring to natural building. And I respect that. I'm just interested in getting more straw into more buildings, but not to ruin natural building. Keep doing the hands in the mud job out there when you can. I really love that stuff. But so that's that project. Here's the millions and millions of CO2 that we think this product has potential to save if implemented in a reasonable pace and adopted well. I can talk more about that. I'm learning how to make business pitches on product development startups. World I didn't think I'd get into, but I want to also talk about our work with low carbon concrete and stabilized earth systems. So I was part of the working group that developed the very first low carbon concrete building code that was financed by Marin County in California, but can be adopted by any region. If you have ties to your building department, you're interested in trying to get a version of that adopted in your area, I can put you in contact with the right people at the Carbon Leadership Forum Institute or the Ecological Building Network. Bruce King really led this effort. And so we hit that spec very hard and do our best to be there, to be the part of the three-way conversation that needs to happen between contractors, batch plants, concrete batch plants, and engineers, which typically through the years just hasn't really happened. An engineer is like, I need this strength. A contractor calls up the batch plant, says, I need this strength, but I'm stripping it pretty early. And so a batch plant just sends them a really, really high Portland cement mix that they can strip super early and read that strength. But nobody asked the engineer if they needed that strength right off the bat. And oftentimes it's not. And you can, and we already mentioned fly ash and slag, supplemental cementitious materials, SCMs, that a lot of people are like, oh, I want a 70 mix or 50% mix, but you just shouldn't care about how much fly ash or slag you have. It's a conversation about how little Portland you have. That's what matters. And because the Portland is the thing that's by far the dominant carbon contributor in the conversation. And then I want to just talk about stabilization too. Stabilization is a word we use when we put cementitious like materials in earthen wall systems. Adobe typically uses either cement or emulsified asphalt. Emulsified asphalt's kind of like fly ash and slag, where it's considered to be a carbon neutral material because it's a byproduct. And everybody we can happy to talk about like how good that is, or I consider it a stepping stone. And anytime I'm working on an earthen building or any building that's super high carbon, I like to try to look at what we're learning about it and why it's part of the journey to a carbon neutral, or, in the case of straw and hemp, a carbon storing, a carbon negative future that we're trying to head to. And but yeah, Adobe uses cement. CEB's pretty dominant cement. Some people use lime, which has actually a similar carbon embodied carbon amount. I asked the CEB folks why they don't use emulsified asphalt, and everybody said just because it stinks and they don't like to. So I think there's like some material research, real material research potential between the materials. Rammed earth is almost all, and now CEB stabilizes, Adobe stabilizes just to keep them safe, like during transit. There's a number of Adobe plants. It used to be a big thing down in New Mexico and Arizona. There's less of them now, but transporting to site and having them arrive safely. CEB stabilizes because if you get the compressed block wet, it kind of can expand. And they really want to prevent that. Where rammed earth stabilizes because you love that striation finish, and you want that to be able to weather and you don't want to plaster over it. And a lot of these materials we plaster to protect the wall, and the plaster is the strong exterior face. But here you want your wall itself to not be weathering. So that's why they stabilize, and they do mostly cement. When you're up above 5%, especially up at 10%, you're probably using as much, if not more, carbon than if you just built a concrete wall. And so that's something to be aware of. It doesn't mean you're not making a good step in the right direction, like I said, a stepping stone to the future, or that you have other reasons to do it. It's just make sure you're aware of it, and don't let anybody kind of, as earthen builders, we shouldn't be greenwashing either. So another kind of thing that's not talked about much is that mass wall and mass insulation is great. Here's this table and a map from the International Residential Code. A lot of other codes have these similar maps where you see the mass wall R value column there, which is less than the wood frame wall R value column. And it's because they give credit to the mass wall and say it needs less, but they don't say it needs zero insulation. And cob walls in particular, when you're at a high density cob wall, we found that they have an R value of 0.22 per inch. And that's 0.22 compared to the 4 per inch generally that your fiberglass, your rock wool, all your conventional insulations have. So it's radically less. But as you go down in density, that insulation increases, and at some point you turn into what's referred to as light straw clay, which is a very straw heavy mix with much less clay, and it's just an insulation, where cob is a structural material. But light straw clay is kind of the hempcrete version of straw and clay, whereas hemp's hemp and lime, and just an insulation that's built around studs for the most part. But be aware of the thermal requirements in your region, and make sure you're building smart and not over crediting the value of mass, especially in a cold region. And that's something we talk a lot about in the book, that people, there's a lot of people out there that have built houses and realize they just need to be burning that fire constantly in these northern latitude regions, because their mass wall, as much as it sucks up the cold and the heat in the Midwest, it sucks up just cold when you're in a cold place, and there isn't a lot of heat. So testing, we're constantly searching the globe for good quality tests. Here's some tests we credited that were from France and England for the hempcrete code, that helped us justify the 24-inch on center spacing, which was something we were having a lot of trouble with negotiating with the ICC. It's not easy to test these materials. Testing costs a lot of money, and oftentimes, especially when you're dealing with like a mass wall system, they're heavy. They take a long time to dry, and every single time, no matter how much we've told the lab they need to think about this, that we're building a 5,000-pound sample, they get there and they go, "Can you believe our forklift doesn't pick this up?" And it's like, "Yeah, I know. I've done this before. We tried to tell you your forklift's probably not," and they special order a forklift in. Here's some fire samples tests we did down in Bryan, Texas, about a year and a half, 2 years. Gosh, maybe it was well more now. The ASTM E119 test is how we rate fires. When somebody says I got a 2-hour fire rating, the original Cobb code proposal was turned down because Cobb, as you know, it's a monolithic, it's a generally non-combustible material. It's what we make ovens out of and have for history. But the proposal was turned down because we were crediting a 1-hour fire rating, which is about the fire rating of drywall and wood studs. And because we were citing some tests that were completed in New Zealand by a different standard, they were fine with our structural calcs for this very low strength, high mass material. They turned us down because the non-combustible material didn't have the right fire test. So we went and we got one. I think the lab fees were like $20,000, and a lot of us donated a lot of time to make this happen. But we only got a 2-hour fire rating because you have to choose the fire rating. You don't want to fail, and almost nothing in the United States on a residential scale requires more than 2 hours. But we think we could get an 8-hour or more test on this. Results here, they for 2 hours they heat. There's my team, Art Ludwig and Laura Bartels, and Jess Shockley she's down in Austin. She was one of the builders, great young builder down there. If you're ever in the area, you should get in contact with her. And Art and Laura are wonderful people too. If you don't know about them and their work, the Art really was got the funding for the test and everything, but they heat the inside of the wall up to 2,000 degrees for 2 hours. The outside of the wall, this was a 12-inch thick cob wall, changed by less than 5 degrees over the 2 hours, which was a lower rise than the concrete slab of the floor during the sun cycle of the day that day. And so it performed incredibly well. Then, part of the process is they give this cowboy this hose and he blasts it for 2 minutes, and there was chunks falling off. I thought we were going to crash and burn at that point. They're still loading the wall structurally with a superimposed load, but it succeeded. You can see us smiling there. And it was this nice red clay that the front layer did vitrify and was blown off by the hose, but the hose is to demonstrate, ideally you're just trying to survive the fire. And I think structurally that you could replaster all this and it would perform for most residential situations. But you can see that yellow straw there, even right behind that thin vitrified layer. It was still just golden and fine after being blasted for 2 hours. Here's some of our tests down with Cal Poly down at Quail Springs, and up at Santa Clara. The late Dr. Mark Ashheim contributed a lot to the testing of straw bale natural. Unfortunately, died young in 2019 of cancer, and a big loss to the community. But we were testing, in plane forces, mostly with seismic in mind, but wind matters too. You just need to prove that your material can resist your wind loads even in low seismic zones. But these were our rocking shear tests, where we had no reinforcing steel in these walls, and we did not, obviously, we didn't anchor them into the foundation. And we found that these natural, unstabilized, unreinforced cob walls were, tied together enough to completely lift off the ground. And this is something that I don't think there was any researcher I've worked with that this was their expectation. And so this means that you can just run the simple physics equation of the force required to lift it up, and now the resolving force of this is where rocking shear comes in. The resolving force of its mass and weight already lifted off the ground that wants to come back down is now working against this higher earthquake force. And that's the next frontier, something we're working very closely. I mentioned Terran robotics before. We get to work with UC Berkeley on the straw panel. We're staggering our studs in this system to decrease thermal bridging. They got a lot of big, dirty but fun structural toys to mess with down in their labs, and it's fun to get the data and things. Sometimes the work in the middle of it is not that exciting, but what's testing is next. If anybody knows someone going to grad school or with some resources and wants to engage in this, there's an endless amount of tests that really have not been done. The concrete industry and other industries with all kinds of special interest money, they fund these tests again and again for universities to do, and they pay these grad students. But these non-proprietary materials don't have that benefit. And so if somebody's interested in an idea, something I think that would be very practical, something we could maybe get into the code or start using on permitted designs right away, or you have an idea and want some feedback on it, I'm engaging with those subjects all the time. People write me, and there's a lot of potential. What's next? Looking to do some hemp research with Penn State University, actually my alma mater. I grew up near there. The Super Adobe Institute, Cal Earth Institute down in Southern California, is hired Martin Hammer and David Eisenberg and myself. I haven't mentioned Martin Hammer and David Eisenberg. Martin was on the photo and the codes, but they are the masterminds and really like the people who originally drove the way for all these natural building codes to get into the ICC. And they've been doing this work for a long time. And I'm happy to put anybody in contact with them if you have specific questions or want to get engaged in any way. We just started a committee with TMS, the Masonry Society, which is the reference code for all masonry engineering designs done in the California Building Code. Oh, I had this slide earlier, so we don't need to talk about it. People contact me all the time about ideas to make stock plans that make getting permits for these systems easier. This is one that was developed for Butte County after their terrible fires a few years ago. These are cob buildings, but it's not easy to do stock plans because you got to think of every situation at once, and then you engineer one building, and everyone seems to want to change designs once they get a stock plan. They're like, okay, this is great, but I just want to move that one wall, or maybe way more than one wall. And for an architect, it's easy to move one wall. The paints don't change. But for an engineer, you might be totally messing up the entire lateral system or gravity bearing system, in which case the value of having a stock plan kind of gets just thrown in the garbage because you sort of have to rework a whole lot of things. And if you put it in a place in a geographic loading situation that it wasn't designed for, I guess I'll just say again, I wrote this book if anybody wants to grab it. I think it's going to be really valuable, not just for cob building. But I'll send you that link, and I'll say thank you for having me, and happy to answer any questions. But if you think of questions later, you're welcome to write me and email me. That's my email address. I can put it in the chat too.
I
Yes.
have a question for you.
Yeah.
If you could allow screen sharing, stop your screen.
Yeah. Did I? No, it's over here. Oh, y'all were talking about domes. We were doing these bovidas with James Anthony recently too. I had this up, but that was a fun project. I don't know if y'all know him, but his work is great. You might know him, Harry. I don't know.
So this is what I push for a lot of people. I was curious if you are aware, and if you I push this for anyone building any house to save money on foundation. This is a federally recognized system so that you don't have to, there's a little example here. So you don't have to build a foundation. 48 inches would be like Montana or something. Normally you have to build past your frost line to prevent frost heaving. But with this frost protected shallow footer system, you can save a lot of money on concrete that you'll never see under the ground by making your footing system no more than 14 inches, but you have to insulate around the foundation. Massive money saver in foundation. I was curious if you were aware and if you use this system with people to save money on not needing to go so deep.
Yeah, thanks, Harry. Can I share screen again?
Yeah, let me get out.
It's a great idea. And also I was the lead proponent for the expansion of rubble trench foundations in the building code, which the building code calls them crushed stone, but the natural building world, and also like Frank Lloyd Wright and the history of that system dates back to like they also use the word rubble trench. But some people think gravel trench would maybe be the better term. So we have these three terms that all mean the same thing: rubble trench, crushed stone, gravel trench foundation. But similar idea. I think that's a great system, Harry, and worth using when you can. And there's also the wood. So if I share here, I feel like I pulled up David's. No, this is the wrong tab. Where was I? Here are the advancements of the crushed stone system in the IRC in the 2024 edition, meaning that you just need to take your concrete a little bit beyond the grade kind of to protect your stone. And here I have a design that we often use these, especially when people are using an earthen floor or want to disconnect their interior slab. Then we see this is pretty shallow. I recommend a little bit more depth than that, 6 inches down. And then if you need to get down to competent soil, or you need to get down to soil depth, you can do it with your crushed stone instead of just a hunk of concrete. While you have this concrete cap, similar to Harry's system, you still have that nice concrete right at the base for your wall to anchor into, your building department to kind of sleep well at night about. And using, especially if we're talking about stabilized earthen materials, there's a chance that many regions don't even need to switch to pure concrete at that point. We talk about when that's appropriate or when it isn't, but protecting from water. But then the folks in the desert that are building a lot of natural buildings are like, why can't we build our cob walls down to the ground? And you probably can, but nobody's studied it enough, depending on situations. But yeah, so that's that system that Harry mentioned, and the crushed stone option are really worth knowing. The crushed stone was only in the code for precast concrete foundations, which are a really weird thing that I don't think anybody does anymore, and wood foundation systems, which is another alternative foundation option that's in the International Residential Code that a lot of people don't know about. It's not for high seismic zones and not recommended for high seismic zones, not permitted technically in the code. But like I said, I do a lot of alternative material work through 104.11. So things that aren't explicitly permitted or mentioned in the code, I'm still used to working with. But the wood foundation systems, I don't have a picture of that up on my desktop right now, but it's worth looking into. We had a thorough design. It was even a basement, retaining basement for this what's that challenge, the building challenge, green building.
The living building.
Thank you. Yeah, they were getting the living building challenge. It was a 2-story straw bale building in Michigan, outside of Detroit, and they ran into some budget issues, and they axed the wood foundation below, but they kept a straw bale building. I don't think they're going for the living building anymore. But we had the design complete, and for lower seismic zones like that, I think it's a good option. Thanks for bringing that up.
So the question for that system is it basically the same as concrete, but you're allowed to use gravel instead to go down to the frost depth?
Right. Because
Okay.
you just need something competent that can bear to get down to frost depth or competent soil. But you don't need like bending strength to get down there,
Right.
or the other things you get out of concrete that you don't get out of gravel. Yeah.
Yeah. That was actually a system I was considering using, because my building, the guy in charge of the building codes here, building department, he recommended the gravel. The same stuff that I use for my driveway. He said I could use that gravel, pack it in there, compress it, and I'd be good to go. But I like the idea of not having to go that route at all. But the only issue with the system I just showed is you have to have an R30, 4 feet horizontally out from your foundation, and R15 up your foundation. So as long as you have those two values, 4 feet out or 30, up to the foundation or 15, you're good to go with that that other system, frost shallow depth footer system.
Yeah, that's great.
Also, speaking about test, I just recently, a couple weeks ago, sent these 4 samples in to be tested for R value. And so this was I did this for people who were looking to use alternative materials for insulation, and the structural engineer needed these numbers so he can uh, you know uh, uh, account for them in the build. So for aircrete, for the lightest mix I could make, I got 1.5 per inch. The styrocrete, which is the came out the best, 2.04 per inch. My epic is 1.41. And this was a custom mix that a customer of mine made and I sent in also. And since I got the 4th mix sent in, I got a better, the more samples I sent in, the better the price was to have tested. Basically, I paid $1,000 for each test, and I have the stamped certified structure R value engineer certificate for all these samples. So I wanted to share this if you wanted to use these samples, I have the paperwork and I offer them on my website. So you could purchase this on my website and you could submit this to your structural engineer to use. And then, under the certification shows the exact recipe for each one. So you could replicate it exactly.
Yeah, that is fabulous. Thanks, Harry. Yeah, thanks for doing that work and offering that. I appreciate that. Wow.
And I wanted
So
to ask if you are familiar with this other material. I mentioned it. Oops.
So I just want to be sensitive to the timing here. I know Anthony has to get going to his next engagement.
Which is my 2 3-year-old twins that just woke up from nap.
Yeah. Well, that's really important. But if there's any final questions for Anthony, I think we could throw them out there and maybe we can keep talking even though you have to take off, Anthony.
I just wanted to know if Anthony was familiar with this product that will turn any concrete into waterproof concrete.
Oh yeah.
Practitioners use that, but it's not really in detail that I need to be engaged with. It's a serviceability topic of waterproofing. So I've heard of those types of materials, but I'm not an expert on them.
Okay.
And you mentioned other materials too. I didn't even mention like our work with mycelium structural products and Occamworks and things. But like I said, there's like probably anything that might come to mind, we probably are screwing with.
I am just super curious why, I haven't seen any testing yet for magnesium oxide cement as a stabilization for earthen materials. And then otherwise, if we're going to go into the whole thin shell cement reinforced walls, I think it's a great option for less material it could be very ecological. And then why aren't we using magnesium oxide cement for that? And maybe there's a reason why, maybe the lack of familiarity, or I'm not sure, but I have a lot more questions for you. I know we're going to have some time in the future. We'll sit down and hash it out, but it seems like, there's just a lot of really great things to try right now.
Yeah, in short, I think it's just that science is young, or the practical application of that science is young. As I've understood about magnesium cements, the potential for them to be very green is out there, but the way that we have to do them right now, it's only a little bit better. Yeah, I have a Google Doc we made for a company that hired us at one point on those. But yeah, we're working with Geodomes right now, who's doing a kind of similar bioceramic.
And then, for 20 years, it's like I'm talking about cob buildings. A lot of my structures are, these more radical, rogue, unpermitted buildings out in the sticks and everything. And it's like, I know that it works. They stand up. I mean, I got no doubt that anything I've built, will stand up to the earthquakes whenever they happen. And so there's that. I mean, just the question of, like, if you wanted to build in a seismic area with an unstabilized earth and material like cob, why can't you just make the walls thicker, and then optimize and have it buttress kind of get narrower as it gets taller, keep everything one story, or these types of strategies where you're really just using the material at the performance of that material has a certain output, and so we can design it for that. And I think it's just a lack of familiarity. Again, they want to see the rebar in there just because, I guess, or maybe there's other structural reasons, but
you're on. I hope that all of our professional lives we see, like the knowledge of earthen matrix mix design, optimization, and section modulus or shape, manipulation advantages, fully utilized. Right now, there's just so many variables that are so understudied that, and you mentioned just make the walls wider. It was my first cob building that this issue, slapped me in the face pretty hard, that mass times acceleration equals force. And so just making the walls bigger, like you do with most structural materials, it also adds problem as it normally adds a little bit more benefit than it adds problem, but it's still adding problem because the wall's mass itself, when you're talking about seismic zones, is the problem. So more of it isn't the answer necessarily, but better use of it is. And it's time and time again, we have these great ideas. We build something that's a circle, a great shape, pipe's really strong. But then here we are, humans cutting windows and doors in it, and then you got a half circle, which is still strong, but not nearly as strong. And so you come up with those compromises, and then domes and things, really strong shapes. But in order for us to analyze them properly, it takes a structural model, and then that's a number of grand more than most people kind of want to invest at the scale that people are looking at these projects right now. And it's not that I don't want to do them, it's just that I'm paying employees, and the investment to kind of like fully analyze those shapes is complex. But once we get a lot of them under our belt, it'll get easier and easier, and we're working on that right now. But these are the kind of things that you're spot on. The future has, I think it will be full of great ideas like that, and we're just one step at a time trying to get there.
Beauty. Yeah, and we should mention, of course, just briefly that there have been some seismic testing processes for earthbag and the super adobe and cob, where they built, I think, a scale model, maybe half scale or something. They built it on a shake table, and as far as I know, I mean, both of the models performed really, really well. The super adobe dome outlasted the shake table itself, so it was good up to a 9.5 earthquake or something like that. It was like beyond what you normally even see. And that's part of the reason why so many counties in California are okay with the eco dome invented by Nader Khalili. It's a small super adobe dome shape. And so, there's the performance is there on a lot of these. And I think, as far as the extra mass goes too, I mean, some of these buildings, they kind of just stay in place while the earth shakes underneath it, there's a certain degree of that. But yeah, the cob buildings, when they shook the cob building on the shake table, it did crack, but the monolithic cob was able to sort of hold itself together because the cracks were irregular shapes and it didn't collapse. So
Yeah, that British Columbia test performed really well. The half scale cob test that you're mentioning, and the other one did as well.
Thank you, Anthony. I really
Yes,
appreciate your time, and we'll be in touch. What a guy. Thank you.
that sounds great. Yeah, thanks for listening, everybody.